Hi all, I'll be presenting our paper Seeing in Low Light. Myself Nisha Verghese, I am from IPCV Lab, IIT Madras, India. Seeing in low light addresses underwater image and depth recovery in low light. So we have a dark underwater image. From that we have to get the depth map and restored image simultaneously in real time. Here you can see one example. The first image shows the low light underwater image. From that we have to get the restored image and depth map simultaneously in real time. So the motivation is in underwater as we go deeper or at night time, ambient light will be less. So the captured images will be having darker radius. Those images can be considered as a low light underwater images. So normal low light image enhancement or depth estimation methods devised for terrestrial images struggle on low light underwater images. Then underwater image or depth estimation methods are there devised for normally lit underwater images, but they struggle on low light underwater images. There are works for restoration of low light underwater images, but no attempt to jointly recover both depth and clean image from a low light underwater image. So ours is the first work that gives depth from a low light underwater image, and there is no dataset with low light bright light underwater image pairs for training. So we captured our own dataset with stereo pairs. Here we can see our dataset description. Here we have 10 video sequences. Each sequence contains one set of videos. One is with low light underwater image and the other is with normally lit underwater image. And we model the scene geometry through illumination independent scene reflectance, unlike existing works. And we proposed a masking scheme to prevent moving transient in affecting the training process that I will be explaining later. So we used a combination of written X theory and underwater image formation model. The normal underwater image formation model can be written as like this: I of x equal to JTD plus 1 minus TB into A, where I is the input underwater image, J is the scene radiance, TD and TB are transmission map corresponding to direct signal as well as a backscatter signal, and A is a global background light. Retinix model tells that scene radiance can be considered as the product of reflectance and illumination. So reflectance is the property of the object, so that will be invariant to the illumination. So this scene radiance can be written as the product of RL and LL. So the low light underwater image formation model can be written like I of x equal to RL LL into TD plus 1 minus TB into A. Here we consider the restored image as the reflectance as the restored image, and the transmission map and depth are directly related using an empirical formula. So depth map is derived from the transmission map analytically. So this is the proposed network. This is used for training and testing. Say we have two images from camera 1 and camera 2. Camera 1 captures low light underwater images. Here we adjusted the exposure settings of the camera to capture low light underwater images. So from camera 2 we capture normal light underwater image. So low light underwater image is disentangled into its components like A, RL, LL, TD, TB, beta. Here RL is the clean image that we consider in our work. Then these components will be combined using the image formation model to get IL dash. Ideally speaking, this IL dash should be equal to IL. So we have a loss between IL dash and IL. Then similarly, we disentangle the normally lit underwater image also into its components, and we take the reflectance Rn. Here we are using the reflectance consistency constraint. So this normally lit underwater image Rn, so the reflectance obtained from the normally lit underwater image Rn is warped in the view of the first camera using the depth obtained from the first image and the pose between the two cameras. Since we are using the already set up a stereo camera setup, we know the stereo pose between the two cameras. So using the pose and the depth obtained from the first image, we warp Rn to RL. So we'll get RL dash. Ideally speaking, this RL dash should be equal to RL. So there is a loss between RL and RL dash. So, but since we are using a camera 1, camera 2, which are stereo image pairs, some pixels will be occluded or some pixels will be out of view. So even if we predict correct depth from camera 1, the absence of those pixels in the camera 2 affects the training. So in order to address that, we have used monocular frames also in cell supervision. So this is our low light underwater image. We are using the adjacent frame of the particular frame, that is known as IL plus. So from this IL plus also we obtain the reflectance RL plus. Then as in the case of a normally lit underwater image, we are warping this RL plus in the view of RL using the pose between the two frames. So this pose is returned by a pose net. So but in the case of monocular frames, the problem is that if say we if some moving fishes or moving plants are present, those pixels won't obey the geometry between the two cameras. So those pixels will adversely affect the training process. So in order to remove those moving pixels, we are using a mask. We are using a moving pixel masking scheme. So we make this mask as 0 if the particular pixel is having a higher reprojection loss. So see here in this image, this rope is actually moving. So those areas should be removed during the training process. So so in order to make the loss on those pixels 0, we are using this masking scheme. So this masking scheme actually makes those pixels to 0. So this 0 will be multiplied with the loss. So those pixels won't contribute to the loss calculation. So this is a PSNR, SSIM and RAW or SIMSC. This is the depth quality metric and this is the image restoration quality metric. So with mask and without mask, we can see that our method is having higher metric values. This is the dataset that we use for comparison. The first one is our dataset, and we have used other 4 datasets also for comparison. Then these are the depth estimation method that we use. That we use for comparing with our method. So traditional underwater depth estimation method we have used, and DL based underwater methods we have used. So here we have used self-supervised or unsupervised method for comparing. Then DL based low light depth estimation method also we compared. Then restoration work we consider traditional underwater image restoration works we consider. Then low light image restoration method we consider. Then deep learning based underwater restoration methods we consider, and low light underwater restoration methods also we consider. And these are the qualitative comparisons. So here it is the qualitative comparison of the restored images. Here the last column indicates our outputs. So these 3 rows our output is better than other outputs. And for the third row, this is the output from a UAB dataset. Here we can see the ground truth here, and our output is more closer to the ground truth than other methods. And low light underwater low light image enhancement method actually struggled to remove the haziness in the underwater images. And this is a comparison of depth estimation methods. Here also you can see these are the 2 ground truths for see-through dataset as well as the FLC dataset, and our dataset is our output is closer to the ground truth. And here also you can see this is the depth map estimated from our method for our dataset. So this is actually better. And these are the quantitative comparison. For depth estimation method we have used row and SIMSC as the metrics, and for restoration method we have used 3 datasets. And for images without ground truth we have used no reference metrics UCIQE and UAQM, and for UAB dataset there are ground truth, so we have used PSNR SSIM. Here we can see for depth estimation our metrics are the best values, and for restoration methods we have best values for ULV stereo UCIQE value, and these values are also higher. And when we consider the execution time, our method actually returns both the outputs in 16 milliseconds, so that is more efficient. And useReadyNet also returns both the outputs in 18 milliseconds, but it actually struggles on low lit underwater images. It actually devised for normally lit underwater image. And this is one example for our output for a video sequence of our from our dataset. Here the first image is the low light underwater image, second image is the restored image, and third image is the depth obtained. So both outputs in 60 millisecond for 512 by 512 image run on RTX 3090 GPU. And we attempted 2 downstream tasks on restored outputs, and the first row shows the restored images from different methods, and our method is shown at the last column. And we have used SAM, segment anything model, from ICCP 2023 to obtain this segmentation mask, and we can see that our method has the the segmentation mask obtained from our restored images is better than the other methods. Similarly, the case of second image also, our segmentation mask obtained from our restored image is better. And we have tried depth estimation also from the restored images. So this is our restored image, and this is restored image from a method MMLE, and so depth estimation from our restored image is better than this MMLE. So the conclusions are, our method self-fluid net is fully self-supervised, where only the input underwater images are used for training, and it returns both depth and restored image simultaneously from a low light underwater image. Self-fluid net emerges the best for depth recovery as well as image restoration for low light underwater images as compared to methods devised for normally lit underwater image and terrestrial low light images, and computationally most efficient. And proposed dataset ULB stereo is a first ever dataset that contains stereo pairs of low light and normally lit underwater images. ULB stereo can be used for many applications like underwater low light image enhancement, depth estimation, 3D underwater structure recovery, low light underwater neural radiance field, and Gaussian splatting, etc. So thank you.